Hi, in this video, we'll be talking about Cauchy sequences and I'll give you a characterization of the real numbers that is equivalent to saying that it's a complete ordered field. And so let's start with Cauchy sequences first. So a sequence of real numbers is said to be Cauchy if there exists a natural number such that any numbers larger than this h will satisfy the following inequality such that the difference between the two will be less than epsilon. So what you're trying to capture is the idea of not convergence, but in the case that the terms get very close to one another, even though this Cauchy sequence might not converge. So, but if you're given a sequence such as 1 over n that converges, then of course it must be Cauchy. So we have that lemma over here, but we can first show an example that this sequence is Cauchy. So let's just say we have 1 over n, then we just need to find a number larger than 2 over epsilon, so that 1 over n is less than epsilon over 2 and 1 over m is also less than epsilon over 2. So when you minus them, you can use triangle inequality to make it into addition, and this will show that it's less than epsilon. And so this concludes that 1 over n is a Cauchy sequence. So really you want to capture the idea that two terms are close to each other now. And if x is a convergence sequence, then of course it must be Cauchy, because you know that x is a limit. So if you are given an epsilon, you can find a natural number such that xn minus x is less than epsilon over 2. This means that xn minus xm can be written as xm minus x plus x plus minus xm. So you're introducing the xm minusing off the x again. And we can use the triangle inequality to split this two entities up, which then both are also less than epsilon over 2, and in which case will add up to epsilon. And so this proves that xn is a Cauchy sequence as well. And then if you have a Cauchy sequence, it is bounded. So Cauchy is trying to be like a convergence sequence, but it may not converge, but you know the terms gather together at the end. And so a lot of the properties of the convergence sequences that we have proven can be again applied to Cauchy, like how we say that the properties can be applied to subsequences. So like convergence sequence, a Cauchy sequence will be bounded as well. And you can really use the fact that you can just take the maximum of these terms before h and h plus 1, and you'll show that xn is always less than m. And so now what we want to do is that if we have a Cauchy sequence, we want to prove that there exists a subsequence that converge. So this works in an ordered field M, not just real numbers. But if now you have a Cauchy sequence, and that if there is a subsequence that converge, then you will know that your main sequence also converge to the same limit. So it doesn't need to be real numbers, and we don't use supremums, that's why. But you can really just show this for a general order field. So we now let x be a Cauchy sequence. So there will exist a number h, such that for any pair of numbers larger than h, xn minus xm will be less than epsilon over 2. And since we know that there is a subsequence that converges to x star, then we know that there will be a natural number larger than this h belonging to the set of the index for the subsequence, such that xk minus x star is less than epsilon over 2. And then we just apply the triangle inequality, because now we can take xn minus x star, it will be xn minus this term xk plus xk minus x star. And then you use the triangle inequality to break them up, and you result in being less than epsilon. And so because epsilon is arbitrary, we can prove that the limit of xn is x star, and hence the sequence is convergent. I hope this is clear to you, and this is actually quite an important result. because now you know that if you can just find a subsequence that converge, so maybe this subsequence is easier to prove convergence, and your main sequence is easier to prove that it's Cauchy, then you can immediately tell that your main sequence converges and to the same limit. And next idea that we want to point out is that because we know that not every field has a sequence being Cauchy is convergent, we have a special type of field, and this field will now be known as Cauchy Complete. So Cauchy Complete fields are that if every Cauchy sequence is convergent. And so that if you are just given a field that someone tells you is Cauchy Complete, and you now can prove easily that there is a Cauchy sequence, then that you know that sequence must converge because the field is Cauchy Complete. And really, we can actually show that the least upper bound property implies that the field is Cauchy Complete. And that really means that R is Cauchy Complete. And so a sequence of real number is convergent if and only if it's a Cauchy sequence. So really this statement is trying to prove that the real numbers is Cauchy Complete. So we already know that if it's convergent, then it's called Cauchy. So now we have to use the other property of supremum to prove that if it's a Cauchy sequence, then it's convergent. And so let X be a Cauchy sequence. And then we know that this Cauchy sequence is bounded. And so by the Blazano-Weierstrass theorem, there will exist a subsequence that converges to some real number. And because we have a subsequence that converge, we apply the proposition that we proven earlier to show that the main sequence will also converge since the main sequence is Cauchy. And thus we have proven that every sequence that is Cauchy is convergent. And hence, this shows that the real numbers is Cauchy Complete. So this really helps us determine whether a sequence is convergent without testing for a particular limit value. And we can just check the Cauchiness of the sequence. So an ordered field that is Cauchy Complete is the real numbers, and a non-example of course is the rational numbers. And you can think of many examples of why the rational numbers is not Cauchy Complete. And with that, we have come to the point where we can now characterize the real numbers in three different ways. So we can say that it has the least upper bound property, and we can also say that every monotone sequence which is bounded converges. And we can now also break it down into two properties. Having the least upper bound property means you're Archimedean and that you are Cauchy Complete. And this characterization now, while we'll not prove it, is important in helping us now construct the real numbers from the rational numbers that is a different type from Dedekin's cut. And really you can read Rudin's for Dedekin's cut, and this is really known as the Cauchy completion of the real numbers, which you can read online for a more elaborate understanding about it. But really, now that we are just dealing with the real analysis part, we really want to talk about the characterization of the real, and these three really formulates are all equivalent. Furthermore, we can also show that any ordered field that has the least upper bound property will be isomorphic to the real numbers. And so we can just talk about this, we can just take this field that may not be the real numbers, but because it has the least upper bound property, we can just say that it's the real numbers. And so that's why in Bertley and Schubert, everything they deal with is real numbers, but you can actually now pinpoint which points are using the least upper bound property and or which points are not, and in which case those propositions that are not can be applied to a general ordered field. And so with the least upper bound property, really being Archimedean means that natural numbers is unbounded. So you need to have a lot of numbers. But at the same side, you want the numbers to have Cauchy sequences being convergent. So you can't have too many numbers also. You need to have numbers that branch out together. And this really is trying to capture the idea that there is always a supremum, means every subset has a least upper bound. And so I've come to the end of characterizing the real numbers, and so now you understand what does a complete ordered field means. When ordered field is a set that has a total, it's a field that has a total ordering, and this ordering respects addition and multiplication. And this complete is trying to capture least upper bound, but you can also say it now captures the Archimedean and Cauchy complete property as well. And so I've come to the end of this topic about real numbers. In the next one, we will continue our journey into real analysis, where we will have a starting point about extended real number systems before video 11 about functions. So I've come to the end of this video. I hope you have enjoyed it. Feel free to like, share, and subscribe, and I'll catch you in the next one. Bye.